Well, good afternoon. It's 2:33. We're 3 minutes late getting started for our differential equations class, Math 238. And by the way, it's the 6th of March, 2019. Unfortunately, I'm the only one in the classroom right now. Hopefully some more will be coming in. But let's go on and get started. I'll wait and do announcements until some people get here, because otherwise I may be talking to the wind if no one is listening to these things. So no reason to take up class time that no one's going to hear something. But I'm going to go on with the class because we got to get this covered. All right, my memory is that we're starting 2.5 today. I think that's correct, though I have a mark at the bottom of the page, and I think that was left over from a previous term. So I believe we're starting at 2.5. Okay, we're in Chapter 2, which is first order differential equations. 2.5 is substitutions or solutions by substitution. Now, a little bit of background here. This is from the top of 72, page 72. We usually solve a differential equation by recognizing it as a certain kind of equation. And I've been trying to do this all along. Is this separable? Is this linear? Is it exact? Is it, whichever, okay? And then we carry out a procedure consisting of an equation-specific mathematical steps, okay? If it's a linear equation, then you locate your p, get it into standard form. Locate your p, integrate the p, raise that to, e, that type of thing. Those specific steps that comes out with some type of solution. But it's not uncommon to be stumped by a differential equation. Isn't that an understatement? Because it does not fall into one of the specific classes that we know how to solve. So now we're going to do some substitution procedures that may be helpful and may not be helpful in working this out. So here's what the substitutions are. Often the first step, solving a differential equation, consists of transforming it into another differential equation by means of substitution. For example, let's say we had dy dx equal f of xy. Okay, that's very generic. Okay. Now, what if we could do a substitution, say y is now equal to g of xu, where u is now regarded as a function of the variable x. Okay. If g, and this, it literally, even right at the beginning, sounds like you're running in the circles. Here you got y, which was an independent variable, being depending on x and u, but u is also a function of the variable x, so you've got it all down to everything is dependent on x, okay, which is what it should be. If g possesses the first partial derivatives, now here we're doing partials again, though we're not doing partial differential equations, okay, then here's where we're going with that. Okay, so let me write down again sort of the givens here, because it's sort of hard to keep up with who's on first here sometimes. So here is our differential equation in some sort of a generic type form, and that's dy dx, there's your derivative, is equal to some function of x and y. Okay. Now, for some reason this is going to be problematic or difficult to solve the way it is, so we want to try a substitution. So the substitution is going to be y is some other function, g, of x and u. Okay? Now, with this, obviously, and I said something a little wrong before, y is not an independent variable, it's the dependent variable. Okay? X is your independent variable here. So this is f as a function of the independent variable x and may have y's in it as well. These y's may not be separable. They may not be linear. They may not, there may be all sorts of problems with it. Okay? Well, then let's try a substitution. Let's try some y is some other function of x and u, but x is fine because that's the independent variable, but u needs also to be dependent only on x. Okay? So, that's where we're starting here. Okay? Now, if g, this g here, that we're doing the substitution, possesses first partial derivatives, then by the chain rule, here's what we got. We're looking for dy dx. Okay? Well, what is dy dx? Okay? It's the and it seems like they left something out here, which is pretty significant, what they left out here. They left out, okay. Just looking at this, not at this, sort of ignore this for now, okay? Just looking at this. Dy dx would be the partial of g with respect to x times dx dx, which we know, of course, is 1. So why they even wrote it, I'm not sure. And if g was a function of, well, that's plus the partial of g with respect to u times du dx. Okay? Now, okay, guess that's okay. Now, the dx dx is 1. Okay? So writing this in another notation, I don't know why they're changing, g sub x, that's a partial of g with respect to x, plus partial of g with respect to u, du dx. I'm so sorry. That came as a surprise. Okay? Times du dx. Okay. That's your dy dx. Okay. Now it says here, if we replace dy dx by the foregoing derivative and replace y in f of xy by g of x u, okay, then the differential equation that we had above, this one right here, we're going back to that one now, becomes this. This thing is being replaced by this. So this will be g sub x plus g sub u du dx is equal to your f of xy, okay? And that we're going to write is f of x. Instead of y, we're going to write g of xu. So, I'm so sorry. I may have to go clear my head because I can hardly breathe now. So, this is what that upper equation becomes when we plug this thing in for the dy dx here, and then this in for the y part of your f down here. This is what you get. Okay. Who's on first? All right. Now, if you solve that for du dx, that becomes your differential equation now. You've gotten the y's out of the picture here, and now you're dealing with u. Okay? Now, this du dx first subtract g sub x from both sides. Okay. I'm so sorry. And then we're going to wind up dividing by g sub u. So you're going to wind up with du dx. Here's your new differential equation, and doesn't this look so much easier? F of x g of x u minus g sub x, partial of g with respect to x, divided by the partial of g with respect to u. Oh yeah, that looks so much easier. But perhaps these things are easier to calculate than what the things were before. We'll see. Okay? Now, that can be shorthanded to be some function, some other F function, we'll call it a capital F, of a function of x and u alone, not x and y. Okay? Now, since we don't know what any of these functions are, this isn't really making a huge amount of sense. So guess what they're going to do here? What if we get a solution which u is going to be some phi of x, okay? Why not introduce another variable in it? It's just another function that, of this last equation. I'm so sorry. Then the solution for the original differential equation would then be this. Y is that g function that we haven't identified yet, but it's some function of g of x, and u is now this phi of x. Isn't this getting exciting? Okay, there is your solution. Okay, in the discussion that follows, we'll examine 3 different types of first-order differential equations that are solvable by means of substitution. Something like this. Okay, now, if this seems like they're going around in circles, it sure does, okay? Here they just keep naming one thing after another thing after another thing. It helps if you have some real functions there. So let's talk about some of these, okay? And the first we're going to do is homogeneous, sometimes homogeneous, okay? I've heard it pronounced both ways, equations. So let's just suppose that your function f possesses this particular property, that f of tx ty is equal to t to the alpha f of x y. Now you might say, where in the world would that come from? Well, if your function has that characteristic, then it's called a homogeneous function. That's for any real number alpha, for some real number alpha. Okay? If that's the case, then alpha is said to be homogeneous of the degree alpha. Okay? So here are some examples. F of xy is equal to x cubed plus y cubed. Now, if you imagine that as a function that showed your d, f that dy dx is equal to this, x cubed plus y cubed. Not separable. If that were multiplied, yes. Added, no. Okay? Not linear, not by a long shot. Okay? Not exact. No. Okay? It's not even, what was that other thing we did just briefly there? I can't think of the word for it now. But, yeah, nothing we have had is going to make that work. None of the techniques so far. Okay. But, now, homogeneous, or homogeneous, what do we mean by that? That your total powers for every variable in every term is the same. Okay? That's basically what your homogeneous means. They all are at the same thing. And that's of degree 3. Okay? Okay? Because what if we did f of tx, ty, that would be tx cubed plus ty cubed, whatever's in the parentheses, inside here, you plug in there, and that's what you get. And this would be t cubed x cubed plus t cubed y cubed, which is t cubed times x cubed plus y cubed, which is exactly your t to the alpha, where alpha is 3, times f of xy. That's exactly what we've got here. So this would be of degree 3. Okay? Now, let's change this ever so slightly. F of xy is equal to x cubed plus y cubed plus 1. Not homogeneous, not homogeneous at all, because that third term is not at the same degree or power that the other two are. Those are both to the third powers. This is to the 0th power. No way you could get that to work. None. So that would not be homogeneous or homogeneous. Okay. Now, a first-order differential equation in differential form, such as this one, this looks familiar, does it, of xy dx plus n of xy dy equals 0. Now that's how we started off our exact differential equations. But it was only exact if the partial of m with respect to y is the same as the partial of n with respect to x. So this is homogeneous if both m and n are homogeneous functions of the same degree. Okay? So both of them would have to fit this thing up here. Okay? And the alphas would have to be the same for each of them. Okay? Now, in addition, if m and n are both homogeneous, in fact, meet that criteria up there, okay, then we can also write, and this is a clever little substitution, so we're assuming m of xy and n of xy both are homogeneous. Follow that pattern, okay? And we'll talk about this in just a minute when we see examples, meaning their total degrees are the same for your variables. I'll explain that in a little bit, okay? Then we can rewrite this m of xy as this. M of xy is equal to the x raised to the alpha, okay, now it was t before, now it's one of the variables raised to the alpha, times m of 1 y. Okay. I'm sorry. That was a t, not x. I was wondering how they did that. I just couldn't read. What they're doing, though, is changing this and also changing n of xy to be t, has to be the same alpha, remember, times n of 1 y. Okay? Now notice what we've done there. Oh, I'm sorry. Sorry. These are not y's. I don't know where my brain is today. I'm thinking one thing but doing something else here. I'm trying to move to the next step. This is new variables u, not y. Okay? Now how did we do that? We did this by the substitution. U is equal to y over x. Okay? Now, This is kind of a, take my word for it, believe me, okay? It's saying if they are homogeneous, you can come up with, in other words, if the total powers are the same, you can come up with a new variable that sort of consolidates the power, okay? Because if they're the same power, then there are going to be some similarities there. The ratios are going to be constants, you know. So, or if it worked out better to do this, m of xy is equal to, and remember these are assumed to be the same, so t of alpha times m of v1 and n of xy is t alpha times n of v1. In this case, our substitution would be v is equal to x over y. Okay? So, what was on top before, your x, it's now the u, I mean, or what was on top before was the, that's not quite the best way of saying it. What was here, the y before, if it's on top here, then that becomes a u, the other becomes a 1. Okay? If the x came first, whichever one you do, then v is x over y, the v takes the place of the x, and the other becomes the 1. Okay. That's what I've been trying to say, but just not finding a very good way to say it. You can rewrite both of these, this one as being y is equal to ux, this one v is equal to, x is equal to vy. Okay. One touch, yeah. Yeah. Like that there too, just in case anyone else wants it. By the way, we finally got a student here, so I'll take a brief pause here to go over a couple of announcements. And one, hopefully this will ease mind a little bit. I can't say this for absolute certain. I just had time to briefly scan emails today. I've seen nothing about midterm progress reports yet. But that was a quick scan, so I may have missed it, but I've seen nothing yet. Right now, the big panic is they sent out several different directions of how to do summer schedules. And so they're a total mess. So right now they're focusing on getting that mess straightened up. And I don't think they're focusing too much on midterm progress reports now. That doesn't mean they won't tomorrow or maybe later today, but right now, just to clear that up, which it sounds pretty simple maybe to you, but to me it's a huge pain because I saw it was a mess at the very beginning. I sent one email saying, look, this won't work, and then that's kind of where the mess started by, do them this way, and I said, that won't work, and I think some other people said that won't work, but unfortunately some other people did it the way they said. Okay, and then when we said, no, this won't work, they said, oh, you're right, that won't work. Well, then do them this way. Well, those people who had already done them didn't see the second ones, and so they still got them one way. This other group has them the other way, and then yet a third way is how we did them last year. And none of the three are anywhere close to each other. So it's a huge mess.
Did AT&T recently buy Lawson State? Because it sounds a lot like AT&T.
Not that I know of. Okay, I'm not sure AT&T would want to buy Lawson State, but yeah. Okay, it's so I have a feeling we're going to be toying with that for a while. And then here's the bad news to follow up with that. One bit of, and this is all to do with me, or a lot of it is to do with me. We ended first mini term yesterday. Okay, today's the second mini term. We talked about that. I have a new class starting tomorrow, but I finished one yesterday. And in that class, awfully close to half the students didn't have everything turned in. So I checked this morning and said, when are these grades due at by? And they said, Friday. Well, that would be great if it was a normal Friday, because Friday I have 4 hours of office hours. I could get as much as I could straightened up of that, emailing students, seeing where their stuff is, doing whatever. And working on straightening up summer schedule, however they've decided to straighten it up, which I haven't even read the email to see what that is yet. But this Friday, I'm driving to Mobile. And so I have no time today to do any of this, no time tomorrow to do any of this, so I've got to do everything I can here, there, and everywhere, and no way I'm going to get all of it done in time. So, yeah, okay. So I've lost Friday as my time to get anything done, and we've got an awful lot to do. So I'm not too worried about the midterm progress reports yet. So let that relax you a little bit if it needs to. Okay, I think that covered most of the issues. If you know of anyone who did take a first mini-term course, please remind them that they need to do their student course evaluation for the first mini-term, not the full-term course, just first mini-term. I doubt if you are in touch with that many. Okay, so what we're doing, we've just been through sort of a mess. We're on page 72, and I basically got one page covered before you came in. It was just at the bottom of the page where we're talking about these substitutions. Okay? Now, and it's going to be really hard to go back and do it all. The first half of the page was on a different screen, so that's not even here. We're looking at substituting to make things work. For instance, okay, we've had separable differential equations. If you got that, by all means use it. This is simple, straightforward. However, if they're not separable, ask if they're linear. If they're linear, set it up in the standard form and then use that technique. But if it's not separable or linear, is it exact? And then there's a test to see if it's exact. Try that technique. They gave this example here. Now, they use this term in two different ways. In this section here, we're talking about homogeneous equations. That's not the same as we're going to talk about them later. Okay? Later, we're going to be talking about higher order differential equations that are homogeneous, very different from what it means here. What it means here, and this is a weird definition, that if your function f of x, y has the feature that if you do f of xt, comma f of tx, comma ty, that turns out being something that's exactly t to some power times f of xy. Now looking at that says nothing to me except, okay, when would that ever happen? Okay. Well, here's when it would happen. They give this as an example. What if this function f of xy, which could be the thing over on the side, dy dx is equal to f of xy. What if this is a function like this, x cubed plus y cubed? Not separable. And if that was times, yes, separable, but not plus, not separable. Not linear because of y cubed. Can't be linear. Okay? Exact? Don't think that'll ever happen. Okay? Because if you wrote this as dy dx equals this, the Your dx would be times this, dy would be times 1. No, that's not going to work either. Okay. But this is what they call homogeneous or homogeneous, because what if you had alpha ty, tx, ty? Well, whatever is here, you cube it. Okay. Whatever is here, you cube it. Okay. Well, if you cube this, you got t cubed x cubed, and you cube this, you got t cubed y cubed. Factor out the t cubed, there you have a t cubed times x cubed plus y cubed, which is your alpha of xy. So this is homogeneous of order 3. Okay. Now, they do all this blah, blah, blah about it. What it gets down to, if you have a function, the sum of all the exponents for your variables there are the same in every term. That's what makes it homogeneous. Homogeneous means same, right? Homo, same, you know. Yeah. Why didn't they say that? You know, I don't know. It would seem like a much simpler way to say, if the sum of all the exponents in all the terms, the exponents for your variables in all the terms are the same, then it's, yeah, you can do this. Okay?
So they would all have to be squared, or they would all have to be cubed, or they'd all have to be...
Yeah, or, I mean, xy squared. That would work too. Yx squared would work, or y cubed. You know, that the sum of your exponents is the same. I think that does the same thing. And then they give the example here, change this ever so slightly, add a 1 to it, it's now no longer homogeneous, or homogeneous, because this one is degree 0. Okay, so that's out of the picture. Okay. Then they jump a new rabbit, just out of nowhere, say, what if you have an expression like this? M of xy dx plus n of xy dy is equal to 0. Hey, that looks like our exact differential form. But it's not exact unless the partial of m with respect to y is the same as the partial of n with respect to x. And something like that, probably not going to be the case. So if that's not the case, what do you do? Well, here is where they come up with their what ifs now. Let's imagine that this m of xy and n of xy are both homogeneous with the same degree. So every term of the m and every term of the n, the sum of your exponents of your x's and y are the same in every one. Then you can change this m of xy to be, you know, it's set up here, it's the same as t to the alpha m of xy. Yeah, okay. M of tx, m of tx, ty would be this. But now they say, what if this m of xy is homogeneous, but now not in xy, but in u, where u is y over x, or change the m of xy and n of xy too, by the way, both of these, to v1, and it's homogeneous, but v is y over u is y over x, v is x over y.
Did you just pull those out in here?
Yeah, or some body part we won't mention. Okay. So,
Top of your head.
yeah, that's it, off the top of your head. That's exactly what I was thinking. Okay. Now, you can take this, multiply both sides by x, and you have y is equal to ux. Or down here, you can have multiply both sides by y, x is equal to dy. Okay. Either one of these, whichever seems to float your boat, which might make it look like it's simpler to do. These are all forms of the same thing. So that gets us to the bottom of this page. Okay. Now, if this will reduce that to separable first-order differential equations, you got it not. If it will work, try it. Okay. Now, wish I had more room to write on this page. I don't. So I'm going to pick up on the next page. And to show this, observe that as a consequence of, I just erased it, the second statement down there, no, the first one down there getting them to 1 u's where u is y over x. Okay. Here's your m of xy dx plus n of xy dy equals 0. Now, it looks like it's exact, but we're going to assume no, it's not, but that it is homogeneous. The m of xy and n of xy homogeneous to the same degree. In other words, the alphas are the same. So if that's the case, now before they were putting I wish I had that screen back. I would point something out to you, but I can't anymore. They went from T's to U's once they went to the substitution. And that sounds really bizarre here. But here's what it turned out to be. From before, x raised to the alpha, m of, now this becomes a 1u, okay, dx, plus x to the alpha n of 1u, oh, yeah, they are keeping the dy's here, which is strange in itself because there is no y anywhere else in the problem, but we'll leave it like that, okay? Or if you use the other substitution, remember that's the y over x is equal to u. The other one was x, oh, I'm sorry, that would be y to the alpha then. No, they're not going to do that. Sorry. I thought they were going to show both of them. They're only going to show one. Okay. Now, if you, this doesn't seem fair at all. If you just imagine you divide out the x to the alpha, then you have m of 1u dx plus n of 1u dy is equal to 0. Now, I don't think that sounds very fair at all.
I don't like that at all.
Okay, but they say this is the same as that. It can be written as this or that. And again, you still got, oh, I'm sorry. I wrote that as du thinking it should be, but no, it's a dy still. Okay. Now, here's the substitution that allowed that. Just to remind us, u is equal to y over x, which is the same as y is equal to u times x. All right. Now, to get yourself into the right framework here, think of when we first did the linears, how they started with the mu, and they integrated and the raised to e's and stuff like this, and it was all mystery meat for a long time. And then you saw, well, this is the pattern. When you have it like this is what you do. So this is, where are they getting these things from? But this is all that stage of it. And then at the end, which hopefully is coming up fairly soon, you'll say, oh, so this is what you do in this situation. So don't get too hung up because these are all abstract right now. Okay? Now, remember, I'm not liking that dy. Okay? Well, let's take this and do what dy is. dy is equal to u dx plus x du, right? Product rule. Right? Even though I'm running off the page there. Okay? So let's put that into our this equation up here. Actually, this equation right here. M of 1u dx plus n of 1u. And now we put this instead. U dx plus x du. Finally, we got rid of the dy, and that's equal to 0. Well, let's get our dx's together and our dy's together. So this is m of 1u plus n of 1u. I'm going to put the u in front. U times n of 1u dx plus n of 1u. I'm going to put the x in front here too. Du is equal to 0. Okay. Yeah. All right. Now, look at this. Your variables are x and u being the dependent variable, x being the independent variable. Separate all those with u's from all those with the x's. Okay? So I'm going to divide every term by x to get this out of there. And of course, that won't matter anything over here. And divide by x here. And these others are all dependent on u. So I'll divide this by m1u plus un of 1u. Same thing here. Let me just draw that there so I don't have to write it again. Okay, and now you got a subtraction in there too, but we'll leave them like this for now. What that winds up being, these go out, and this moves over here, and you have dx over x, which I can integrate that, plus n of 1u over m of 1u plus u n of 1u dy. That's equal to 0. Now you can move one of the others on the other side of the equation and integrate. Not dy, du. I think I even said du and wrote y. I don't know. I'm just so used to writing dy. It's du. Thanks. Okay. That same du there. Okay. At this point, we offer the same advice. Don't try to memorize this thing. This has all been done to confuse you. So don't let it. No, they didn't say that. Oh, I misread it. Okay. Do the things as you get to them. Okay. Now, let's do example 1. See if we can work through this procedure. And this is called the substitution procedure. So here we have x squared plus y squared dx plus x squared minus xy dy is equal to 0. Okay. Now, the thing to note, the degree of each term in both of those is 2. X squared, that's x to the 2. Y squared, that's y to the 2. X squared, that's x to the 2. xy, x to the 1, y to the 1, 1 and 1 is 2. Okay. Your total degree and all that's the same. So this is a candidate for what we're just talking about. Okay? Now, here's what their substitution is going to be. One of those that we talked about, let y equal ux. Okay? Now, why they went to all the trouble of doing u equal y, x over y over x, blah, 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 they never use it. Okay? They use this. Okay? Let that be your substitution. Then, dy is equal to u dx plus x du. Good, straightforward. Just a simple product rule derivative. Okay. Now, with those substitutions made, let's rewrite what we've got. Okay? This will be x squared plus, not y squared, but u squared x squared dx plus x squared minus x times ux dy is equal to 0. Oh, but let's not even write the dy there. We don't need it. So let's write that as u dx plus x du, and that's equal to 0, because that's what your dy is. Okay, again, get your x's together, and the dx's together and the du's together. So what this becomes, I'm going to write it out in gory detail the first time. After this, I'll probably skip steps like crazy. X squared plus u squared x squared dx plus, now I'm going to do this thing times that. X squared u minus xu squared dx, right? That's this thing multiplied by that part. You see what I've done?
No, you multiplied by what?
Okay. Multiply this parenthetical part by the part with the dx in it.
Okay.
So it would be x squared u minus xu squared, and all that's times dx. I need a parentheses there. Left off the parentheses. And that means I probably don't need the parentheses there. I put it in the wrong place. Okay. Now, the third part, which is this thing multiplied by this. So this will be plus x cubed minus now wait a minute. Did I write that wrong? I'm getting myself confused here. Oh yeah, wait, no. Yeah, okay, I did write it wrong. This was a x times u, so it's x squared u squared. See, these two x's and these two u's. Okay. I did leave that one off. Okay. Now on the last part, it was x cubed. Oh, okay. X cubed du. Okay, I'm not writing that in yet. Minus x squared times x, so that's x cubed u du. Okay. All right. Now let's combine these two that go with the dx's here. So we have an x squared plus x squared u plus
Wait, stand by. Somehow I wrote that down.
yeah.
Wait, is that right? No, I didn't write that down. Oh, I didn't write. I'll leave you alone.
Okay. Now, when you do that and combine all those terms together, you know, in other words, factor out the dx and then write those together, look at what you got here. A plus u squared x squared and a minus u squared x squared. Okay? So those add to 0. Okay? That simplified things a little bit. And here we have just a plus x cubed minus x cubed u du. Okay. Now, the good news here is this one factors out in x squared. X squared times 1 plus u. I've got my brackets and parentheses all screwed up. Dx plus, and here you can factor out an x cubed times 1 minus u du. Oh, all this is equal to 0. I've been leaving off my equal to 0. Okay, sorry. All right. Now you see we have separable situation here. If we divide this side by 1 plus u, I'm hoping that is, divide this by 1 plus u, divide this one by x cubed, and this by x cubed, okay? What we have now is these go out, okay? Whew. All right. These go, leaving you that. So you have dx over x. That's all that's left over here. Okay? Now I'm going to swap sides and say equal to, and in order to do that, I'm going to reverse the 1 and the minus. 1 minus u and make it u minus 1. U minus 1 over u plus 1 du. Because I moved it to the other side, so I had to subtract it, and by subtracting, I flip these two, left and over there. And I flip the bottom two too, but you can do that without changing sign. Okay, that's separable. Let's see what we can do with it. I can integrate this one. That's log x. Now, this one isn't quite so nice to integrate. What I'm going to do first is divide. Don't have a lot of room, but I'm going to do it. U plus 1 is divided into u minus 1, right?
We're working on the integration of dx.
Yeah, this thing right here. That's written in rational notation. I'm doing division here. The denominator into the numerator, right? Right. Okay. Well, u will go into u once. That gives us u plus 1. Now, normally we subtract. I like to change signs and add, so that becomes minus minus. When you add that, that's minus 2. Okay? Can't go any further, so this is going to be minus 2 over u plus 1. Okay. 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 I'm dividing this into this. I start on the left. U will go to u one time, then multiply. 1 times u is u, and 1 times 1 is 1. Okay? Then I subtract. But with signed numbers, I like to prefer to change signs and add. So I change that to be a minus and change that plus to be a minus. Okay? So when I add these two, the u's go out. Add these two, it's minus 2. Well, you can't divide any further, so this is your remainder of your divisor, minus 2 over u plus 1. You know, that's how you, when you're dividing fractions, 3 will go into 7 twice with 1 left over, so it's 2 1/3. Right? Yeah, okay. Same thing here, only it's algebraic expressions. Okay. Now, so I'm going to write this integral as that, the integral of 1 minus 2 over u plus 1 du. Okay. Now, I don't have enough room, so I'm going to have to start erasing the top of the page and pray that I haven't made a mistake. Okay? So, I think I'm okay. It's looking a lot like the one in the book. So they didn't change sides, I did. So I'm going to erase this and that. Oh, remind me, y is equal to ux. Just keep that in mind. I probably should have kept that, but I'd already gotten that erased before I realized I probably need it back. Okay. I don't have unlimited papers like you do. I have one little screen here, and it fills up way too fast. Whoa, I lost something. I've wondered how this looks at home, just things start disappearing off the page. Okay. Now, I'm going to write it down again. Y is equal to ux, right? That's what we had, right? That was our substitution. All right, we've got to figure out how to do this integral. So I'm going to start with that. Integral of 1 minus 2 over u plus 1 du. Okay, this isn't too bad. Antiderivative of 1 du would just be u minus 2 times the log of u plus 1. Right?
Yeah.
Okay.
Yeah.
And that's equal to log x, and somewhere we have to have a c in there, you know, our constant, because we just integrated twice. We're going to put all the constants in together. All right, this would be really beautiful if all those were log terms, but that first one isn't, and there's no way to make it a log term. Now, we could get this down to x as a function of u's, but I'm not sure that's the direction we want to go here. And no, it isn't. We're just right where we want it to be, I think. Okay. Now, the only difference is, and they're looking into their crystal ball to know this, we'd rather this be a log C. It's a constant, so you can name it anything you want to. Log C is a constant just as well as C is a constant, so we're going to do that because it's going to make everything a little bit easier later. Okay? And what they're going to do now is go back, and what we had before, y is equal to ux, but now we're going to u is equal to y over x, which is where that came from to begin with, right? Okay, so we're going to unsubstitute now. We got rid of the y to deal with the u's and x's. Now we're going to come back to y. So this will be y over x minus 2 times the log of y over x plus 1 equal log x plus log c. Okay, remember, log c is just a constant. It's just a strange way of writing the constant. All right, let's get this over common denominator in there. So let's leave the y over x by itself, minus 2 times the log. Let's get this over least common denominator. Okay, least common denominator would be x, so that would be x over x, right? That's 1. Okay, so this would be log of x, or y plus x, I don't know which way, y plus x over x. It's equal to log x plus c, log c. Okay. Now, something that's magical about logs, let me make sure. Okay, I know they do this one. Y over x is equal to let's do the, no, not equal to, minus the log of y plus x over x squared. Remember, that's one of the rules of logarithms. A 2 in front of a log can become the exponent of the argument of the log. Okay. And that's equal to log x plus log c. They love that log c. Okay. Now, what we're going to do next is isolate the y over x, get all the logs on one side and the things without logs on the other side. So this will be y over x is equal to, we're going to add this to this side, this is log of y plus x over x squared plus log x plus log c. Love that log c. Okay. Now these you can combine all together because the sum of logs is the log of the product. That's another rule of logarithms. That's how slide rules worked. Did you ever use slide rule? Never. Okay. When you're multiplying big numbers are really hard to mess with. So you take log of a big number, it's a lot smaller. But when you take a log of the big numbers, and if that's a product of several things, that's the sum of their logs. That was another one of, it's really from the same thing of this doing that, because this is the same as log of that plus log of that. That's the log of that thing squared. Right, okay, so. I don't know if they do it this way, but here's how I'm going to do it. I'm going to call this as log of y plus x squared. Now notice I'll lose the absolute value bars. You know why? When you're squaring this thing, it's always positive. The only reason you use absolute value, you can't take the log of a negative number or 0. So we're assuming this will be work. Okay. And then this would be minus log, whoop, 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 whoop. I just see something I forgot. This, oh no, that's right, okay. I already took care of the two, okay. Minus log x, because that x squared, because that was in the denominator. But you know, I'm going to take this around and make it a 2 log x again, in reverse. Plus log x, plus log c, okay. Now that, okay, so y over x is equal to log of x plus y, y plus x, x plus y, it doesn't matter, squared, minus, and here's a minus 2 log x plus log x, so that's just minus log x plus log c. That's why I changed it back. Whew. Now, they do something really bizarre here. I've lost where they are.
Where did your
okay.
Negative 2 log x, where did that go?
Okay. All right. Oh, I separated these and made it log of this thing squared minus log of this thing squared. Okay. But once I got that separated, I brought the 2 down in front, just like I moved the 2 here up here. I brought it back down and made it 2 log x plus log x.
So, which is negative log x.
It makes it a negative log x. Now I see something I've done that they didn't do in the book, and I'm sorry about this. I'm going to go back and change it all. Remember I said that plus, they always do this to me, that the constant was a c, and then I made it a log c. I want to make it a minus log c. It's still a constant. Plus or minus is just a constant. And make it this. The reason for that is going to go back and connect again, and this will be y over x is equal to log of x plus y squared. And then I'm going to put this as minus. Now, the log of a sum is the sum of two logs is the log of their products, okay? Again, that same type deal we were doing before, okay? So this becomes minus the log of cx, okay? Now, because that's why I had to make it a minus sign, so I could get those same sign. So this becomes y over x is equal to, now let's combine that. That puts it back in the denominator. Log of x plus y squared over cx. Now I can exponentiate both sides. I think I'm doing it in time. Yeah. But I'm out of room again. So I think I will. I don't think I need this bottom line anymore. I sure hope not. But you've got it written down so we can retrieve it if we need it. Okay. So let's exponentiate both sides. It's e to the y over x is equal to x plus y squared over cx. Okay? And then multiply both sides by cx. So x plus y squared is equal to cx e to the y over x. Okay. And that's our solution for this. Back in x's and y's. Certainly not something you can write as an explicit solution. This is an implicit thing. There's no way you can do it. But this gets it all done. And the one parameter system, there it is, because this is just started off being a first order differential equation. Okay. No way that could have worked any of our other techniques, but by making a judicious substitution because it was homogeneous, okay? All your terms on both sides, the sum of the powers were always the same. So we could do this substitution. And it was actually either one of two substitutions. The substitution really was u is equal to, y is equal to ux. Okay. Now, if that doesn't work, you could try x is equal to vy. And that could work. Now, where in any of this did we ever use m of xy, m of 1v, m of x1? Not a place. Why in the world throw that into the mix way back there when you never see it again? Okay? Really, that's what we were doing. We were making that substitution, but all that was just confuse factor in my mind, you know. But it does work out okay. And we did all. Came okay. Now, that's the first kind of an equation that's substitutionable, okay? It's a homogeneous equation. And that's the technique you use for that. And I think we're just about out of time, so aren't we?
Yeah, we got like 3 minutes.
Okay. I don't think we're going to have time to do Bernoulli's equation. So that's where we'll start next time, and not where we didn't start this time. Now, we only got basically 2 pages done, but this was a pretty complex thing. Bernoulli's equation works a lot the same way, but it's slightly different, so we'll see that. Once we finish Bernoulli's equation, then we got numerical methods, which is not it's one type of a numerical equation. There's certainly ones that are better than this, and we'll talk about that. Now, I got your test ready, and just in case we did get more covered today, But I take it you probably don't necessarily want the second test while you're still working on the first?
I've got the first one here. I'm turning it in.
You are?
It is what it is.
Okay. Okay.
I'm still having trouble with one of them. So,
Right.
But
Okay.
I'm okay with the grade.
Okay. Do you want the second one? Anything we haven't covered yet, which is Bernoulli's and reduction to separation of variables, which I thought was what we just did, but it wasn't necessarily homogeneous. We haven't done those two, and we haven't done numerical method. If you want it to start working on it, you can, or if you want to just wait until next week when we get this covered.
If you got it, I'll go ahead and take it.
Okay. I thought you might want to do that, and since you're the only one here, you have that option. Okay. And the number 4, which is the biggest part of the test, you obviously can't answer any except the ones that are separable, exact, linear. Now you can do homogeneous. You can't do Bernoulli yet because we haven't done Bernoulli, but you can do the others. So you may have some blanks left that you can't fill in. You can do the first 3. Now, let me just tell you what to do on the first one. That's separable. Go on and separate it. See what you come up to. Once you have an answer, then see what the K can or can't be. So don't try to guess the answer before you actually do the work. Is what I'm saying. Okay. This one, what you need to do is write that as piecewise function. Y prime is equal x for x greater than 0 minus x for x less than or equal to 0. Yeah. Write it that way first. Then solve each of those differential equations, okay, because you've got 2 of them. But then you plug in this one with the one where it's less than 0, because -1 is less than 0. Do that, and then use that same constant you come up with, for your for the other one, and you'll get that one done. Again, we can work through some of this. Oh, and remember when we did autonomous. And this sounds like a really hairy problem, but it really isn't so bad. Go back and review that autonomous. I think you'll see linear and nonlinear is a real simple way to deal with that. So now let's see. I think most, except some of these blanks you can do based on what you know already. But then from there on, wait till we get the rest of it done. Especially Euler's method. That's the next section. So after we get the last part of this done and Euler's section, then we can finish that. Okay. So don't panic over it yet, because some of the stuff we haven't done yet.
Okay.
Okay.
And then I'm going to turn this in.
All right. Good deal. Thanks.
So.
And I don't know when I'll get to grade it, knowing that what I do know now about how much I've got on top of me right now, but I'll try to get it graded.
By the end of the semester, I don't care.
Okay. All right. Good deal.